Hi, welcome back. In this lecture, we are going to look at time domain eigenvalue calculations. And in the second part of this lecture, we are going to study the stability analysis of a finite difference scheme. In the previous lecture, we saw how to solve eigenvalues problem using finite difference, but in the spectral domain. In this lecture, we're going to look at how to solve eigenvalues problem in the time domain. When we solve the eigenvalue problem in the time domain, the workflow is divided in three parts. There is a time loop that requires the calculation of our electric field or magnetic field values at each time step. So what we do is to time step a solution. For instance, we can use a simple finite difference program. At each time step in this time loop, we can record the field values at different location of our domain. So we are repeating our loop at each time step. We calculate the new electric field. Then we select some electric field values at a certain point and record as the time is evolving. Once the time loop is finished, we can apply the last step of our workflow, that is apply the Fourier transform to the signal. So I remind you that we record the signal in different points of our domain. Once the time loop is finished, we take this array with a history of electric field variation in different locations, and we apply the Fourier transform. The end result of this calculation will be the calculation of eigenvalues that are obtained by applying the Fourier transform on these signals. In the previous lecture, what we did was to calculate the eigenvalues and the eigenfunction in the spectral domain. So this is the problem that actually we solved. We solved the Helmholtz equation and then we calculated the eigenvalues and eigenfunction. Today, what we're going to do is to calculate the eigenvalues but in the time domain. So we're going to move to the time domain. So in this specific case, we're going to have the second order derivative of f in time equal to an operator of f. It might be, for instance, the curl operator. So what we know from the previous lecture is that we can formulate this continuous derivative in discrete formulation. So in this part of the slides, you see the discrete formulation of the second order derivative in time. In this case, n is an index for the time step. And so the new time step is called n plus 1. The current time step is called n, and the previous time step is going to be n minus 1. Since we are going to use a second order approximation, not only we're going to need the values of f at time n, but also at n minus 1. And then we have the second part that is still keeping the part of applying the operator on the function f at time n. So one important point about this formulation is that the time stepping is explicitly. That means that no matrix inversion is needed to compute f at time n plus 1. As you can see here, what we need is just the values of our function at the previous time step n and the previous time step, that is n minus 1. So these time stepping schemes are often referred as leapfrog. They're very efficient because they just require the values from the previous time steps and allow the determination of complete eigenvalue spectrum. An important issue for explicit time stepping schemes is how to choose the time step delta t. So a question we might have is, well, can we use any values for delta t? Well, the answer is no. So there is a criterion that is called stability criterion. So when we do stability analysis, we need to introduce a so-called amplification factors rho. So the analysis that we're going to do is based on the fact that any discrete time equation, which has no explicit time dependence, has the solution on the form depending on the eigenvalues and eigenfunction of the problem. So our solution at the time, our solution at time n is going to be at our function f omega multiplied by rho, that is our amplification factor, to the power of n. So this generates a geometrical sequence in discrete time, since we have rho to the power of n. So we're going to have these geometrical sequences. As I told you, rho is called the amplification factor of the eigenmode f omega. So when this fn grows, well, this fn grows when rho is larger than 1. So this will be crippling close with the time. So in order to keep our solution bound and not make it grow as geometrical sequences, what we are going to do is to require, for stability reason, that our amplification factor, the absolute values of our amplification factor, is less or equal to 1. So we keep this solution bounded. So how this working? Well, the first step is substituting our function at the time n with the eigenfunction f omega multiplied by amplification factor rho to the power of n, where n is the time step. So we're going to plug this expression here in our explicit leapfrog update of function f. So we take this function, we're going to replace fn as in this way here. We can also replace this expression here, f at the time plus 1 at the time n plus 1, and we can replace also this expression here. A second thing is to recognize that we are still solving an eigenvalue problem, so we can replace this expression for the operator with minus omega square of the eigenmode that is associated to that particular eigenvalues omega. After applying this substitution, both using the amplification factor and using the fact that we are solving an eigenvalue problem, we obtain a quadratic equation for the amplification factor. So we can just replace and then we divide by f omega, and we divide it by the amplification factor to the power of n minus 1. So if we do this arithmetic operation, we obtain an expression for our application factor. So this is a quadratic equation. We know how to solve the quadratic equation, and here we have the solution of this quadratic solution for the amplification factor rho. So let's look at when rho, the amplification factor, and in particular when the modulo, the absolute values of rho, is less than equal to 1. So remember, when rho is less or equal to 1, the numerical scheme is stable. So the roots stay on the unit circle, that is a circle when rho is the modulo of the application factor is less than 1. So this is true in our equation as long as the modulo of omega delta t is less or equal to 2. However, when the absolute value of omega delta t is greater than 2, one root has modulus larger than unity, so we are in this region here. This means that the solution will grow exponentially in time because our amplification factor has a power of n. And the scheme for the time step is called unstable. So this is a plot in the complex plane. Here we have our circle that denotes the stability region of our scheme. Outside this area, the scheme is unstable. So since the absolute values of omega delta t needs to be less or equal to 2, has to hold for all the eigenvalues, all the eigenmodes. For this reason, we select what is the highest eigenvalues here, since the other ones will be really smaller. So we take the stability condition by keeping the highest eigenmodes here, the highest eigenvalues, and we retrieve a time step stability condition on the time step. That is, the time step in our problem needs to be less than 2 divided by the absolute values of the maximum value of the eigenvalues of the problem. We can also apply in the same technique in the space. So when we have only the time, then we need to take 2 over the maximum eigenvalues of our problem in time. We can also apply the stability limit to the spatial operator, for instance, the second order derivative in space, discretized on a uniform grid with the cell size h. So the largest numerical eigenvalue is going to be 2 over h, and the stability requires that delta t needs to be 2 over omega max. In this case, the omega max from the grid is 2 over h. That means that delta t must be less than h. So this is also called current condition. The time step for our simple explicit scheme for the wave equation should not be larger than the space step for stability reasons. So this is very important stability constraints when we have derivative both in time and in space. So in the previous slide we saw when the derivative is in time, that is, we can gain a stability condition on the time step when the equation combines both derivative in time and in space, both the second order. Our stability condition is delta t must be less or equal to the h. In the final element chapter, we'll also study implicit time stepping scheme, which make possible to remove the stability condition. Those schemes are called unconditionally stable. But when we have finite difference and no implicit time stepping, we're going to always have a stability condition. In this case, delta t must be less equal to h. This was the last slides of this lecture. In the next lecture, we are going to look at how to solve numerically the eigenvalue problem in the time domain. Talk to you soon.